So in this video, we're going to be looking at the sine, cos, and tan, so the primary trig ratios, for what are called special angles. Special angles are multiples of 45 degrees, 30 degrees, 60 degrees, 90 degrees. We'll see a few examples of those. So if you plug into your calculator, say if we're doing the 45 one, sine of 45 degrees, you'll get a decimal answer usually on your calculator, depending on the type of calculator you have. Sometimes it'll actually put an exact answer for you, but often most calculators do a decimal answer, something like this. You'll get 0.707. But what is the actual exact answer for that? That's what we're going to solve today. And we're also going to prove why those exact answers are the way they are. So we're going to do a little bit of proving. So how we do this, if we're looking at the 45-degree angle, first we just draw 45 degrees on our unit circle. 45 degrees is the angle between the positive x-axis and the terminal arm. So that's 45 degrees in there. And you can see it should look like 45 degrees. And then we draw a line that goes straight down from your point and goes straight down to the x-axis there. And a line that goes across there. So the green line here is the y value of that point, and the purple line is the x value. Let's look a little bit closer at this triangle. It's a right angle triangle. We know that all the angles in a right angle triangle add up to 180. So this angle in here must be 45 degrees, right? Because 45 plus 45 plus 90 would all add up to 180 degrees. If those two angles are both the same, those are both 45-degree angles, that tells me I have an isosceles triangle here. So this guy here is isosceles. So that means that the two sides must be the same length. Whatever value the y is here is also going to be the value of the x side here. So we could call them both d. And then what we're going to do is try and figure out d. The reason why we're doing that is because this side d represents the y value, which represents sine of 45. So if we can find d, we found sine of 45. And this purple line here represents the x value, which is cos of 45. So if we can find d, we've also found cos of 45. So to solve for it, we're actually going to use the Pythagorean theorem. The Pythagorean theorem would be a squared plus b squared equals c squared. So that's your two sides close to the right angle, which are both d squared. And they add up to your hypotenuse squared, and your hypotenuse is 1 there. So that was a bit messy. I'll make that look better. 1 squared. Good. Let's simplify this a little bit. D squared plus d squared is 2d squared. And 1 squared is just 1. And then we could divide both sides by 2. And that gives me d squared is equal to 1 over 2. So I could square root both sides, and I'll get d is equal to the square root of 1 over 2. That doesn't look very pretty, so maybe I'll write it as root 1 over root 2. The square root of 1 is just 1, so I can write d, sometimes I struggle with writing on a tablet. Here, d as 1 divided by root 2. Right, the square root of 1 is just 1, and then the root 2 I'll leave as root 2. I'm leaving it as an exact number here because that's the whole point of special angles, is to write things as exact numbers. So d is 1 divided by root 2. And that is one standard way to write d, but there actually is another way too. So you'll often see d written this way as well. So it's 1 over root 2. But you could multiply the top here by root 2 and the bottom by root 2. And that's legit because it's root 2 over root 2. That's just multiplying by 1. And that would give you root 2 divided by 2. So that's another way you might see d written too, and it's just as good. So d could also be written as root 2 over 2. They're both right. And you'll notice both of them are the number 0.707, and then the digits go on and on forever. But we're not writing it down as this decimal answer. We're writing it down as an exact answer in the form 1 over root 2. That gives us our sine and cos values, right? So if d is equal to this line here is equal to the sine of 45, and it's also equal to d, then sine of 45 must be 1 over root 2. And if this purple line here is equal to the cos of 45, then cos of 45 must be equal to 1 over root 2. So let's summarize that. So cos of 45 is 1 over root 2. Sine of 45 is 1 over root 2. Ooh, what about tan? Well, tan of 45 is sine of 45 divided by cos of 45. So let's plug these in. Sine of 45 is 1 over root 2. Cos of 45 is also 1 over root 2. That's a fraction over a fraction, so maybe I should write it as the top fraction, 1 over root 2, times the bottom fraction flipped upside down. And then you can see the root 2's are going to cancel, and I'm actually just left with 1. So that tells me that tan of 45 degrees is just equal to 1. Try that out on your calculator. Tan of 45 should be equal to exactly 1. We can use this then to do multiples of 45 degrees. So let's say you have 315. Well, that's a multiple of 45 degrees. It's related to that 45-degree triangle. It's just in a different place. 315 degrees, how I draw it is I always start every angle at the positive x-axis. And then if I go that far is 90, that far is 180, that's 270. I go a bit further. That right there would be 315. So that's a 315-degree angle there. And what I'm really looking for is like the xy coordinates of that point at the end of my terminal arm. So I should probably draw a y value here, so sort of a y side of that triangle, and an x side of that triangle there. And the angle in there, the angle inside my triangle, is going to be 45 degrees. How do I know? If I do 360, which is going all the way back to the positive x-axis, minus 315, the leftover bit is that angle in there. That would be 45 degrees. So that's a 45-degree triangle. As soon as I know it's a 45-degree triangle, I know what the two sides are. This side must be D, and it's going to be, which is 1 over root 2. But notice that in this triangle, in this situation, it's actually negative there. And then this purple side is also equal to D, which is 1 over root 2, but in this case it's positive here. So that tells me the cos and the sine of 315 right away. So the cos of 315 is the x component, that's this purple side here. You can see it's a positive number. You can also remember that cos is always positive in quadrant 4, and this angle is drawn in quadrant 4. This is quadrant 4 down here. So right, this is 1, 2, 3, 4, if you remember the quadrant numbers. So we're down in quadrant 4 here. Cos is positive in quadrant 4 because it's on the positive x-axis there. So cos of 315 is positive 1 over root 2. Try that out on your calculator. If you type in 315 and you do the cos of it, you should get positive 0.707, or maybe your calculator will even automatically say positive 1 over root 2, or some will report it as root 2 over 2. All of those are the same thing. The best way to write it is either as 1 over root 2 or root 2 over 2 is also fine. Let's look at the y value. So the y value is this side here, which is also 1 over root 2, but it's negative because you can see you're at a negative value on the y side here. Sine of your angle is always the y value, so sine of 315 must be negative 1 over root 2. And last but not least, tan of 315 is going to equal the sine of 315 divided by the cos of 315. So that will be, sine is negative 1 over root 2, and that's going to be divided by cos, which is positive 1 over root 2. You can keep the top fraction the same, so keep the negative 1 over root 2 the same on the top, but multiply by the bottom fraction flipped upside down. And you can see that the root 2's again cancel, and I'm left with negative 1. So tan of 315 must equal negative 1. And you can check that on your calculator. Tan of 315 is indeed negative 1. All right, going to a more tricky one. So the 30-degree special angle. So we're going to need to find these two sides here. Y will be the sine of 30, and x will be the cos of 30. You can see this time we don't have a nice isosceles triangle. These are not the same size. The y is clearly shorter than the x. But we actually can create a nice triangle by doing a sneaky move. So what we'll do is we're going to actually draw a reflection of this triangle in the x-axis. So we're going to reflect it kind of down here like this. And the reason I did that is because it makes this angle here, now it's like a 30 degree there, 30 degrees there, that would be 60 overall. The other thing I know is that if I look at the original yellow triangle, it has angles 30 in here, 90 here, and all the angles in that triangle have to add up to 180. So 30 plus 90 plus something equals 180. That something must be 60. That's helpful because it's the same down here, right? Because it's reflected in the x-axis there. So what I have is a triangle where all three sides are 60 degrees. Well, what kind of triangle is that? That's an equilateral triangle. And equilateral triangles are really handy because all the sides are equal. So if all the angles are equal, they're all equal to the 60 degrees, then all the sides will be the same length. This one I know is a length of 1 because it's just the radius of the unit circle. This one is also a length of 1, also because it's the radius of the unit circle, but also because all sides are the same length. And because all sides are the same length, this side here must also be a length of 1. That's really helpful because it tells me what y is. So y is just this height right here. Well, if the full height of my equilateral triangle is 1, then y is clearly half of that. So y must equal 1/2. And remember, y is the sine of 30, so what that tells us is that sine of 30 degrees is equal to 1/2. Check that out on your calculator. When you do sine of 30, you should get 0.5 or 1/2. That's handy for telling us what x is. So I'm going to erase some stuff here so that we have room to look at this triangle a little more closely. So for figuring out x, what I have is a right angle triangle again. I know y is 1/2. I know the hypotenuse is 1. I'm trying to solve for x. So what we can actually do here is use Pythagoras' theorem. Pythagoras' theorem is that x squared plus 1/2 squared would equal the hypotenuse squared, which is 1 squared. So that these two sides squared add up to the hypotenuse squared. Let's simplify that a little bit. So I get x squared. 1 over 2 squared is going to be 1 squared divided by 2 squared. 1 squared is just 1. 2 squared is 4, so I'll get 1/4 there. And 1 squared is just 1. Now let's move the quarter to the other side. So I'll get x squared equals 1 minus 1/4. Then I'll just go up here for some more room. So x squared is equal to 1 minus 1/4. Well, that's 3/4. Let's square root both sides. So then x will be the square root of 3 over 4. And I can write that as root 3 divided by root 4, which is handy because the 4 is actually square rootable. The square root of 4 is 2. So x must be root 3 divided by 2. What that tells me is that this side here, this x side, is equal to root 3 over 2. That x side is cos of 30, right? So that tells me that cos of 30 degrees must equal root 3 over 2. That's what that side length is there. Okay, so let's just summarize that. Sine of 30, we did first, that's the y value. That was equal to 1/2. Cos of 30 is equal to the root 3 over 2. And tan of 30 is going to be sine of 30 divided by cos of 30, which is, the sine was 1/2, right, divided by the cos, which is root 3 over 2. So you'll want to keep the top fraction the same, so the half stays the same, but take the bottom fraction and flip it when we multiply, right? So that becomes 2 over root 3. And notice that the 2's will cancel out here, and we get 1 over root 3. So that means tan of 30 degrees is equal to 1 over root 3. And if you want to just check that to make sure you're doing it right, type in tan of 30 degrees into your calculator. In your calculator, you'll see that tan of 30, if your calculator reports it as a decimal, is 0.577. And also try typing in 1 over root 3 in your calculator, like actually calculate what that is, and you get exactly the same thing, 0.577, and that decimal goes on forever. So tan of 30 is indeed 1 over root 3. All right. Let's try a related angle there. So a multiple of 30 would be 150 degrees. If we drew that out, there's the positive x-axis. We always start there to measure our angles. If I'm drawing out 150, go all the way to 90, and then a bit further, not quite as far as 180, would look kind of like this. So that would be 150 degrees there. If I went all the way to 180 and backed up by 30, right, that would give me 150. So this angle in here must be 30 degrees. I got that by doing 180, which is all the way down to here, minus the 150. So let's draw our little triangle on there. There's the point I'm looking for, it has a y value, and it also has an x value. So when I look at the y value here, you can see that this triangle clearly has a short side and a long side. And what you'll want to remember with this 30, 60 degree triangle is that the short side is equal to a half, and that the long side, which is the x in this case, is equal to root 3 over 2. But pay attention to what quadrant it's in to know the sign of that. So here I'm in quadrant 2, right? This is quadrant 1, 2, 3, and 4 here. And in quadrant 2, you can notice that the x values are always negative because you're on a negative x-axis. So that must be a negative root 3 over 2. And if you remember from before when we talked about this, cose is always negative in quadrant 2, and so that fits as well because cose is x. So let's write these down now. So sine of 150 is the y value here. And you can see that that's equal to positive a half. Oh, sorry. Positive a half. There we go. The x value is the cose. So cose of 150 is x, which you can see is negative root 3 over 2. And then to calculate tan, what we have to do is sine divided by cose. So I have to do sine of 150 divided by cose of 150. The sine of 150 is the half. Cose of 150 is the negative root 3 over 2. So once again, I want to flip that fraction and multiply. So I keep the half is the same, but I flip the one on the bottom. So that becomes negative 2 over root 3. You'll want to cancel the 2's. We're left with a negative 1 on top and a root 3 on the bottom. So I get negative 1 over root 3. So tan of 150 degrees is negative 1 over root 3 exactly. All right, the 60-degree triangle is actually exactly the same as the one we just did, just flipped on its side. But because I know that all the angles in a triangle add up to 180, if that's a 90-degree angle there, there's 60, then the last angle must be 30 degrees. So because we've already done all the work for the 30-degree triangle, we don't need to redo it here. I know that the short side of the 30-degree triangle is a half, and in this case, the short side is going to be the x value here. And I know that the long side of this 30, 60, 90 triangle is equal to root 3 over 2. That's what we just proved before. So I don't need to rederive that and reprove it. I can just write it down again. And that gives me my 3 trig ratios for the 60-degree triangle. Cose is the x value, so the x value is here. And cose of 60, therefore, must be a half. So you can check that on your calculator. Do cose of 60, you'll get a half. Sine of 60 must be root 3 over 2. That's the y side here. And tan of 60 must be sine of 60 divided by cos of 60, which is going to be equal to the sine one is root 3 over 2 divided by cos, which is a half. So we keep the first fraction the same, root 3 over 2, and we multiply by the bottom fraction flipped upside down, which is 2 over 1. We'll notice that the 2's cancel, and we get just root 3 over 1, or root 3. So tan of 60 is equal to root 3. When you do tan of 60 on your calculator, you should get the number 1.73. If you find root 3 on your calculator, you'll also get 1.73, and then the decimals go on. That's because tan of 60 is exactly the square root of 3. And the last one is the easiest one. So multiples of 90 degrees. So 90 degrees is here, right? There's the positive x-axis. We rotate 90 degrees. Gets me to right here, so that's a 90-degree angle. So what I'm really looking for is the x and y components of that point right there. It's a really nice point because it's actually on the y-axis. So the sine of 90 would be, well, what is the y value at that point there? And the y value is clearly at 1. So sine of 90 must be 1. And you can check that on your calculator too. Sine of 90 is indeed 1. Cos of 90 is the x value of that point. And that point is at 0, 1, right? So the x value at that moment is 0. So cos of 90 will be 0. Well, then what would tan of 90 be? So tan of 90 is sine of 90 divided by cos of 90. We'll plug in our numbers here. Sine is 1, cos is 0. Oh, what is 1 divided by 0? Well, anything divided by 0 is undefined or infinity. So it turns out that tan of 90 is actually undefined, or it's an asymptote that's shooting off to infinity. And we'll see that when we actually graph the tan function later on too. Try it on your calculator. If you try and do tan of 90, you'll get a math error, right? But that's because it's not defined, because it's a sine of 90 over cos of 90, which is a 1 over 0. Let's try one more multiple of 90. What about 360 degrees? So here's the positive x-axis. If I measure 360 degrees, it goes all the way back to the positive x-axis. So I'm looking for the coordinates of this point right here. You can see that point is going to be at 1 for x and 0 for y. So that means that the sine of 360 is the y value, which is 0, and the cos of 360 is the x value, which was 1. Tan of 360 will be sine of 360 divided by cos of 360. Gives me sine is 0 divided by cos is 1. 0 divided by 1 is 0. So the tan of 360 degrees must equal 0. And if you try that out on your calculator, that should be what you get. Tan of 360 is 0. All right, what you're going to do on this page is just summarize all of these with all the angles, all the special angles in a unit circle. So what we'll do is we'll write them down as points, just x, y points, knowing that the x value is cos of your angle, so x is cos of theta, and y is sine of theta. So whatever angle I'm at, the x value will be cos of that angle, the y value will be sine of that angle. So at this point, you can see the coordinates of that point are 1 for x and 0 for y. So that means when I'm at, this is my angle here. Basically, the angle is 0 degrees. Cos of 0 will equal 1. Try that out on your calculator to make sure you're right. Cos of 0 is indeed 1. Sine of 0 will equal 0. The next angle here, so this one, this is 30 degrees next here. And the coordinates of that point there will be root 3 over 2 for x and 1/2 for y. So cos of 30 is root 3 over 2, and sine of 30 is 1/2. The next angle here is 45 degrees. So just erase some of this stuff here so you can see better. So this is the 45-degree angle next. And the coordinates of that point are 1 over root 2 for x. So cos of 45 is 1 over root 2. Sine of 45 is also 1 over root 2. That's for this point right here. The next point is the 60-degree angle. So this right here is 60 degrees. And the coordinates of that point are 1/2. So x, which is cos of 60, is 1/2. And y, which is sine of 60, is root 3 over 2. And then we get to a 90-degree angle. So 90-degree angle looks like this. The 90-degree angle will be at coordinate points of 0 for x, 1 for y, right? So cos of 90 is 0 and sine of 90 is 1. And then we get into some beyond 90-degree angles here. So the first one we're going to do is related to the 60-degree triangle, right? This will be 60 degrees in here. You can see it's a nice reflection on that side. And that makes us 120 degrees there. At 120 degrees, you're going to be looking at this point here. The coordinates of that point, you'll have to start being a little bit careful about your signs. The x value is actually negative now, so it's negative a half. And the y value is positive root 3 over 2. But otherwise, it's like a nicer reflection of this point over here, right? The 60-degree point, with just the x value being negative. Let's draw the next one. So our next one here is going to be this line right here. You can see that's related to the 45-degree triangle. So it must be 180 minus 45, which is 135 degrees. And at that point, so sorry, this goes with that point there. This one will be here, this point here. At that point, I'm going to have an x value of negative 1 over root 2, right? It's a nice reflection of this point here, and a y value of positive 1 over root 2. All right, so your job is to try and finish filling in this whole circle as you go around to figure out what each angle is and figure out what the x and y components of those angles are.